everybody. So today I want to talk to you about artificial transmutations, specifically two types that are used in, or hopefully soon to be used in, the power industry. And also, when we talk about nuclear weapons, unfortunately, we're usually referring to one of these two types of artificial transmutations. The first one I want to touch upon is the fission reaction. And the way I remember fission is I think of fission division, meaning that what we see here is with fission reactions, a large nucleus is made unstable, and that unstable nucleus will then spontaneously split into two smaller nuclei. Now, how does this nucleus, this large nucleus, usually uranium-235, how does this become unstable? And that is by bombarding that nucleus with neutrons. And so we show here the neutron bombarding the uranium nucleus, hitting that uranium nucleus, and then that uranium nucleus captures that neutron. So there's a neutron capture that occurs. That neutron capture causes the nucleus to become unstable, and then the nucleus will split. Now, there's a couple of important things that are going on here. One of them is that this is a chain reaction. So these three neutrons that are produced, they will actually go back and they will react with more uranium. And so what you get is this sort of exponential growth of collisions. Because if each of these are producing three neutrons, each of these collisions, and then each reaction therefore is producing another three, you end up with this exponential growth of collisions. And you would think that's a good thing because a lot of energy would be produced. But at the same time, though, we want to control this reaction. We don't want it where, all of the neutrons hit all the uranium at the same time. We wouldn't be able to control that release of energy. Now, I keep mentioning this release of energy, and that's something that also is happening. So there is a release of energy. Now, how much energy is released? Well, it's not governed by normal energy terms, because in this reaction, what's actually happening is matter is actually converted into energy. This goes against most of the laws that we have for conservation of matter and energy, but it obeys this law, E equals mc squared, where c is the speed of light. And you don't have to know this mathematically, but the idea is that the matter that is destroyed is converted into energy. That energy is released. So here we have a ton of energy being released. This is much greater than what you would normally find if you were to have just a conventional combustion reaction. So if I were to combust, like natural gas, it would be giving off thousands of joules. With this one, it is giving off so much more energy, like a terajoule. Something to that effect, 10 to the 16th joules, compared to a few thousand joules. So I want you to keep this in mind. This is really the reaction that is used in most parts of, or in every reaction that we use for nuclear energy, where we take the energy that's produced from a nuclear reaction and we convert it into electrical energy. And so, how does this work? Well, here's sort of a schematic of a nuclear reactor, and it shows you the main parts. So inside the reactor vessel here, this is called the core. The core of the reactor contains fuel rods. Now, the fuel rods contain enriched uranium, and this enriched uranium has to be enriched through some kind of process, usually centrifugation. So when you hear in the news about, well, the Iranians or the North Koreans or, any state for that matter are enriching uranium in order to produce um, nuclear power, this is what they're referring to, the idea of enriching uranium for a specific isotope, in this case, uranium-235. The reason why people take issue with this uranium enrichment is because there's different types of grades of uranium. And when you have uranium that is enriched to a high degree, it's considered weapons-grade uranium, and that is not going to be used in a reactor. That would be used for some kind of nuclear weapon. So when people talk about this uranium enrichment programs and their nuclear programs, the United States, they're concerned that other nations are going to be enriching uranium for a weapon. Now back to this, fission reactor though. We have the fuel rods. That's what is going to be undergoing the fission, uranium-235. But like I mentioned before, we want to control this reaction. And so we need something called control rods. The control rods generally get inserted between the fuel rods, and they actually will absorb those neutrons that we saw in the reaction on the previous slide. If there's less neutrons that are available to react, then they won't have this uncontrolled chain reaction. When we talk about Chernobyl, this nuclear power plant in Russia that in 1986 melted down, those scientists were conducting an experiment, and unfortunately their equipment was messed up and they didn't realize that they had completely removed the control rods from the reaction. Since their gauges were off, they ended up where the core was overheating and they didn't realize it. They tried to reinsert the fuel rods, but it was too late, and the core had caught fire, it melted down. Now, something else that's missing from this slide are the moderators. A moderator will actually slow down a neutron. And this actually helps fission. This will increase the neutron capture. Now, where does all of this energy go that's produced? Well, it goes to boil water. So they boil water, they create steam. That steam turns a turbine, which causes a generator to be produce electricity, and you get your electricity. You wouldn't notice the difference if you were getting your electricity from, a nuclear power plant. On Long Island here on New York, we had a nuclear power plant that still exists, but they never actually opened it. That was out in Shoreham-Wading River. There's also Indian Point, which apparently there's rumors that they are closing down Indian Point due to its close proximity to New York City. People are concerned about nuclear power, because of some of the safety issues that have come up. And, when a nuclear reactor unfortunately has some kind of accident, it's usually a big accident. And that accident has long-lasting effects that we'll talk about in class. I don't want to go into it in the video. We'll talk about it in class. This is just a little schematic to give you an idea. A lot of people wonder, where are we getting our fuel from? And, you can see that, most of our fuel here in the United States, 80% of it is generated by some kind of, close to 80% is by fossil fuel. That's coal, that's natural gas, that's burning oil. Then we have these other, renewable sources like hydroelectric, other renewables, which would include things like solar, and those, account for a small percentage. If we compare this to something like Japan, they have a higher nuclear program, although now, due to this other accident that they had, they're probably going to scale back on that. They have a large amount of coal that they're burning, natural gas as well, but then they're also, tapping other renewable sources like hydroelectric and solar. Now their plan is by 2030 or so to completely sort of look at their system and their power production differently. So they're hoping to scale back their nuclear program. They might do more now that they've had that accident, and they're hoping to increase their renewable sources to almost 25%. This is natural gas over here and coal. But you can see like they're hoping to do hydroelectric, wind electric. This PV is photovoltaic. That's solar panels. And so there's this plan to try and, get off of this fossil fuel consumption and also to scale back nuclear. Here's just another schematic for you. It shows how different countries are generating different amounts of nuclear power, and you can see United States by far is one of the largest producers of nuclear power. And then showing you here, this is the capacity that's generated. Okay. We'll talk about this in class, nuclear fission versus nuclear fusion, and also the pros and cons of nuclear fission. Why are we looking at this? I just want to quickly touch upon nuclear fusion with you, another form of nuclear power that is important for us to sort of, understand and look at. And nuclear fusion, this is where we take two small nuclei and we fuse them together. And so when we have these two small nuclei fused together, normally we would work with hydrogen, two forms of hydrogen, one being tritium and the other one just being hydrogen, and we would form helium from this. And we'll watch a video on fusion, but this is very, very hard to do. The idea is to try and produce, helium and energy from this as well. And when we fuse together these nuclei, some mass is lost with the same equation, E equals mc squared. And because of that loss of mass, it's converted into energy, and that energy is then used to, again, it would be used to drive a turbine or to produce electricity. So we'll go through what the pros and cons of fission are, and fusion, and we'll talk about the applications. There's two videos in class I want to show you, one on fission and one on fusion, so you get an idea of what's good and what's not good about it. Now, when we do artificial transmutations, there's other types of artificial transmutations that can occur besides fission and fusion. But a key to recognizing them is that you start with two reactants. And so, for example, I could take something like, something that's not fission or fusion, something like maybe phosphorus 30, and I could bombard it with something like an alpha particle. But you'll see there's two reactants that are reacting with each other. When I see these two reactants reacting, I know that I'm going to undergo something that is an artificial transmutation. To be a transmutation, remember, you have to generate a new element completely. So, this might produce maybe something like sulfur 32. And then it might produce, maybe, so that would be 17 and 16. So maybe it would produce like a hydrogen atom and maybe a neutron. So we saw these in the worksheet where they didn't have one reactant and two products. But again, you need to balance the equation with the right number of, numbers on top and on bottom. All right, so I'm going to stop here because the video is starting to get long. Next time I'll talk to you and finish up artificial transmutations and introduce half-lives. Thanks so much for watching.